Okay, so last week you all worked with springs and Hooke's law to figure out displacements in a spring or to figure out the required force to make a spring compress by a certain amount. This week we are experimentally determining those spring constants that are in Hooke's law. And so when you get to that PhET simulation that I attached in this worksheet and on Classroom, it'll look like this. And for the first part of this week, at least, we're going to be working in the stretch part of that simulation. So I'm going to click there. And when you come into that simulation, it'll look like this. Before I do anything else, I'm going to go ahead and click this unstretched length and resting position boxes. And it'll be clearer what those two things are if I go ahead and add a mass to this spring. And it bounces a little bit. If you want it to stop bouncing and just come to wherever its equilibrium is, wherever this mass's equilibrium is on this spring, then you can click this stop sign up here, and that'll sort of pause any of the bouncing that's happening and just bring it right to its resting position. And so this unstretched length blue line here is up where the spring would hang if there were no mass on it, and then the resting position green line is where the spring rests if there is some mass on it, or for that particular mass being on it. And then when we talk about displacement later, and we'll actually measure this today, the displacement is the difference between where the spring would be with nothing on it and where the spring is with whatever mass we have there. So when we're starting with determining these spring constants, the place that I'm going to ask us to start, that you all have heard me ask you to start ad nauseum for the entire year to this point, is with a free body diagram. And just like we did starting back in November, I'm putting the mass 250 grams right in the middle of that free body diagram. Now, we have to include the forces that are acting on this. And so I'm going to include the force that's pretty much always been there all year, our force of gravity. And if this were the only force acting on that object, it looks like it would just be in free fall. This is going to accelerate downward. But we can see that this object, this 250 gram mass, is at rest. There must be something acting upwards. And in this case, we can see the spring is balancing that force out. It's exerting some upward force, which is able to keep that object right where it is. So we've got gravity force acting down, spring force acting up. I don't think there should be any other forces. This isn't moving, so there's no friction or air resistance. There are no strings really, so there's no tension, no normal force because it's not sitting on any surface. So I think this should be our entire free body diagram for now. Now, we do know from earlier in the year that our force of gravity can be calculated as mg, or mass times gravity, and assuming that we are on Earth, that g will approximate as 9.8 meters per second squared. That's the acceleration due to gravity that you all experimentally determined back in November as well. And so we actually know everything we need to figure out what this force of gravity is. But before we actually do that, I'm going to convert this 250 gram mass into kilograms, because in order for our forces to come out to newtons, which is the standard SI unit for force, we need to get this grams into kilograms. A newton is technically a kilogram meters per second. So let's write our 250 grams over 1. And this isn't something that you all need to show every time you do this. I'm sure that some of you already or will develop just like a quicker recognition way to do this conversion. But just so that you at least know where this comes from, I'll show this one time. So we've got 250 grams in our numerator. Our equivalence is 1,000 grams equal to 1 kilogram. And so I knew to put my grams in the denominator of our conversion factor because we're going to want those grams to cancel out and just be left with these kilograms. And so if we multiply by everything up top, so 250 times 1, and then divide by everything in the bottom, so divided by 1, divided by 1,000, then we should get that our mass in kilograms would be 0.25 kilograms. And I'm going to go ahead and, before I do anything else, I'm going to put that back in the middle of this free body diagram just because those are the units that I want to work with. Those are the units that'll get us where we need to go here. So 0.25 kilograms. So now we're actually ready to go back and calculate that force of gravity. So we take that 0.25 kilogram mass, multiply by the 9.8 meters per second squared acceleration due to gravity on Earth, and we get 2.45 newtons. And I'm going to go ahead and add that to my diagram. Okay. Now, we still haven't figured out anything to do with that spring force yet. And in order for us to determine what that spring force is, we actually need to use the fact that since this object is at rest, this gravity force and spring force need to actually be equal to each other. The magnitudes, even though the directions are opposite, the magnitudes should be the same. And that's why this block can stay stably at rest without bouncing at all. It's just at its own equilibrium. And so if our gravity force is 2.45, then our spring force must also be at 2.45 newtons. Okay, and now we're pretty close to having our final answer. So I'm going to erase this conversion as well as our gravity calculation to leave room for the rest of this problem. But if you want to see how I did some of those things, make sure you take a step and review some of those important preliminary steps. So now that we've got our spring force, we can really go through and apply Hooke's law, which was that the spring force is equal to negative K times X, where this K is a spring constant. That's basically the stiffness of a spring, or sort of the strength of a spring. Over in the simulation, we can control this spring constant by sort of moving this slider along. So small would be sort of the smallest spring constant that this allows for. And then as we increase to sort of the first, second, third, up to this sort of large setting for our spring strength, it gets stiffer and stiffer. For this experiment that I'm going to run, I'm just sort of arbitrarily choosing that we'll do this first one. So I'm sort of counting the small as our 0 setting, 1, 2, and then so on. So we're working on this first notch setting. And the only thing that we know in this equation so far is that our spring force is 2.45 newtons, is equal to negative K, and then we're not sure yet what that displacement actually is. So if we want to solve for that displacement, or if we want to solve for that spring constant, we actually need to somehow figure out the displacement. And we're going to need to use this ruler in our simulation. So when you first open it up, it'll start over on the right side over here. I'm just going to line this up so that the very top of the ruler, or the first sort of line, the 0 line, is right at that blue line, our unstretched length. And then to measure our displacement, we want to measure from this blue line down to the green resting position with the mass on it. And it looks to me, and you might not be able to see to the exact centimeter or to the exact tenth, especially if you're doing this on a phone, but I sort of have a range that is acceptable for answers here. It looks to me like that displacement is about 62 centimeters, and specifically that is 62 centimeters down. So I'm actually going to write this as negative 62 centimeters. Right. So down would be negative, up would be positive. And so then if we come back to this equation, at this point we can sort of think about plugging that 62 or negative 62 centimeters, not meters, into our equation. The one thing that I'm going to need to do first, though, is convert that 62 centimeters into meters. And so again, I'm going to set up a very similar kind of calculation. I'm going to leave out the negative for now just because we'll know that our answer should be negative for this displacement. And our equivalence is that there are 100 centimeters in 1 meter. And so I have centimeters in the numerator right now. If I want those to cancel out and go away, I need to put my 100 centimeters in the denominator and 1 meter up top. Those centimeters will go away. And I need to multiply by everything up top, 62 times 1, divide by everything in the bottom, divided by 1, divided by 100, and we should get 0.62 meters. So now we can actually plug that number in, our displacement, in for the, we can plug that 0.62 meters in for our displacement. And let's now use Hooke's law. 2.45 Newton spring force equals negative K, which we don't know, times negative 0.62 meters. And I'm just going to go ahead and cross out these two negatives because those will cancel out. Negative times negative will just give us positive again. And then to finally solve this, we have to divide by whatever is next to the variable we're trying to get. So we have this 0.62 next to our K. So I'm going to divide both sides by that 0.62 to get that to cancel out. So 2.45 divided by 0.62, and we should end up, I'm going to write it down here, with a K equals, I believe it's 3.9 something, but let me check that with the calculator. 2.45 divided by 0.62 should get us 3.95 newtons per meter for that spring constant. And that's a very similar procedure to what you could do for every notch of this slider for the spring strength. For today, you guys are going to be working really on the third setting. That's where the default sort of starts you at. But you'll follow a very similar procedure. Well, you'll start with a free body diagram, calculate the weight, also known as force of gravity. That's got to be equal to the spring force, and then you measure displacement and use Hooke's law to eventually solve for your spring constant. It's a pretty involved calculation, but I think the more you practice it, the more comfortable that will hopefully get.